Hello class, in this video I'll be showing you an application of Extrema that involves finding an optimal solution. Let's begin. An ecologist is conducting a research project on the breeding habits of ostriches in captivity. To do this, they must construct a rectangular pen with 2 additional fences parallel to its width. Find the maximum area obtained with 4,500 meters of fencing. In part A, we want to define the variables. We will let x be the length of a side length, and y be the length of one side width. Part B, create the constraint function and solve for one of the variables. The constraint is the fact that there is only 4,500 meters of fencing. So I'm going to draw a picture to help create the constraint function. In this picture, x represents the length, and there are 2 of them. Y represents the width, and there are 4 of them. So the constraint function is going to be 4,500 is equal to 2x plus 4y. Now to avoid fractions, I'm going to solve for x. So I'm going to start by subtracting 4y from both sides. And then I'm going to divide both sides by 2. So we have x is equal to 2,250 minus 2y. Part C, create the function that will be optimized. In this problem, we want to find the maximum enclosed area. And the area of a rectangle is equal to length times width, so the area is going to equal x times y. Part D, create the objective function and find the domain. To create the objective function, I'm going to substitute 2,250 minus 2y in for x and create a function of y. That will look like this. Next, we're going to distribute the y. So the objective function is 2,250y minus 2y squared. Now to find the domain. Each side length must be greater than 0. So in the objective function, the first side length is 2,250 minus 2y. That must be greater than 0. So this implies that y must be less than 1,125. The other side length is just y, and that must be greater than 0. So the domain is the open interval from 0 to 1,125. Now to find the critical numbers of the objective function. To find the critical numbers, I'm going to start by finding the derivative of the objective function. That would look like this. Next, I'm going to set the derivative equal to 0. That will look like this. To solve for y, I'm going to subtract 2,250 from both sides, then divide both sides by -4. So we have y is equal to 562.5. Since 562.5 is in the domain of this function, we can conclude that it is a critical number. Part F. Verify that the critical number is the location of the optimal solution and identify the optimal solution. To verify that the critical number is the location of the optimal solution, I'm going to use the second derivative test. The second derivative of the objective function is -4. If we evaluate the second derivative at the critical number, that is also equal to -4, which is less than 0. Since the second derivative, when y is equal to 562.5, is less than 0, there is a relative maximum at y is equal to 562.5. What this means is that the enclosed area is maximized when the width is 562.5. To find the maximum area, we're going to evaluate the objective function when y is equal to 562.5. You can go ahead and do this in Decimus, and when you do, you'll get 632,812.5. So the maximum area possible is 632,812.5 meters squared. And we are done.